Hello, welcome back. So today we're going to continue this series of lectures about solving nonlinear equations with linear algebra. We're talking about polynomial equations. Before we start, let me quickly present myself. My name is Daniel Cabarcas. I'm a professor at the National University of Colombia in Medellin. I did my PhD at the University of Cincinnati in the US under the supervision of Jin-Tai Ding. And then I did a postdoc at the University of Darmstadt in Germany with Professor Johannes Buchmann. And then I got my current position at the National University of Colombia at Medellin. I work in applications of algebraic geometry and commutative algebra, especially to cryptography. For the past 5 years, I've been involved in this NIST competition to standardize new cryptography based on different problems so that it is resistant to attacks by quantum computers. So that's the post-quantum cryptography. And I've been involved in attacking crypto systems. That's what I've been doing. And now for these attacks, I've been using algorithms that use algebraic geometry. And that's what I'm going to be talking about today. So in the previous session, we introduced the basic theory, the classical theory about how to compute Groebner bases and how to use Groebner bases to solve a system of polynomial equations. So let me recap really quick. So the idea is shown in this example. We want to solve a system of equations like this one. We manipulate the equations algebraically to come up with a better way to describe the same solution space. The last equation is written in just one variable. We can solve it factorizing that polynomial to get 3 solutions on the y. We then substitute them back and we find the corresponding values in x. The way to get this kind of system is called a Groebner basis. And the reason we can do that is due to elimination theory. So we define what a Groebner basis is. A finite subset G of an ideal I is a Groebner basis if the ideal generated by the leading terms of G1 through GT is equal to the ideal generated by the leading terms of the ideal. So if the leading terms of the GIs generate the whole idea of leading terms. And we actually got to a point where we show a criterion to check on a finite number of steps if we have or not a Groebner basis. And that's called the Buchberger criterion. And it says that if we have an ideal generated by polynomials G1 through GT, and this is an ideal in a polynomial ring, then G is a Groebner basis. That set of polynomials, G1 through GT is a Groebner basis. If and only if, for every pair of indices, the remainder of division of the S polynomial by G is 0. So if and only if every S polynomial reduces to 0 modulo G. And so what we're going to do today is we're going to continue from this point. I'm going to show you why this leads to an algorithm to compute Groebner basis. Then we're going to see how a Groebner basis is useful to solve a system of equations. And then we're going to start talking about other methods to find a Groebner basis using linear algebra, using Gaussian elimination. That's the idea for today. Okay. So all we have to do to check if we have a Groebner basis is to take every pair of polynomials and check if they reduce to 0 modulo G. And this leads to a very simple algorithm to compute Groebner basis. It's Buchberger's algorithm. And here is a sketch of the basic Buchberger algorithm. Let's say we start with a finite subset of polynomial ideals, of polynomials. And we want to find a Groebner basis for the ideal generated by F. So F may not be a good basis. We're going to improve it. So we first store that basis on G, and we're going to be increasing G until we get a Groebner basis. So first, let's store all possible pairs of elements from G in this set B. Then, while there are elements in B, while the set B is non-empty, we're gonna do the following. We're gonna pick one element from B, we're gonna remove it from that set of pairs, then we're gonna compute the S polynomial of that pair, and we're gonna try to reduce that. We're gonna do the division algorithm of H under G. So we're gonna find the remainder R of dividing H by the basis G, by the current basis G. If the remainder is 0, well, that's it. We're done with that pair. We're good. If not, if the remainder is different from 0, we're gonna add that element to the basis because it means that we found a new leading term. So we're gonna add it to the basis G. And we're also going to consider all pairs of elements from G with the new element R that is going to be in the basis. It's not hard to see why this algorithm will find eventually a Groebner basis. For once, every time we increase the size of the basis, we get a larger ideal of leading terms generated by the GIs. And since the ring is Noetherian, that cannot go on forever. Eventually, this is going to stabilize. And it will stabilize precisely and when it stabilizes, then it's gonna go through all remaining pairs until it runs out of pairs. So this algorithm computes a Groebner basis. Okay. Now, There are many ways to improve this. It's in general, it's not efficient. It's exponential, and it depending on the case, it can be even double exponential. But there are some ways to make it a little bit faster. Until the 90s, researchers concentrated in these 3 ways to improve it. One was the pair order selection. So the order in which we consider the pairs matters. We want to consider first pairs that lead to lower degree polynomials. So there are different strategies to do that. One is the normal strategy, which is to choose a pair with minimal least common multiple. And there are other ways, and there are some improvements that can come from that. Another one was when you get a new element to include in the basis, this element can reduce elements that were previously on the basis. And this can actually remove certain elements from the basis. It may happen that you get a very small leading term that reduces many of the polynomials that are already in the basis. And the basis quickly gets smaller, and you have to consider less pairs. So to do this is also useful, and it leads to important improvements. And finally, there are some criteria to discard some pairs a priori. There are pairs that are known for some reason to reduce to 0. And then we don't have to go through the division algorithm to reduce them. We can a priori throw them away. The point of this lecture is not really this. So I'm definitely not going to talk about the first 2 points. I will come back to the third one later, maybe tomorrow or on Thursday. Because what I want to do now is first explain why a Groebner basis is useful to solve a system of polynomial equations. And then I want to go beyond the 90s and start talking about the new methods to compute Groebner bases that are based on linear algebra, that use large matrices and a massive Gaussian elimination to compute a Groebner basis. So it's kind of a different family. And we then will come back to this criteria, to discard pairs, because they are definitely important in many ways. All right. Are there any questions before I move on? All right. So I need to introduce elimination ideals to explain why a Groebner basis is useful to solve a system of polynomial equations. Given an ideal I generated by F1 through Fm, the else elimination ideal is the ideal in the variables kl plus 1 up to kn, defined as the intersection between I and the polynomial ring in those variables, KL1 through KN. So notice what we're saying here is the ideal only on the last n minus L variables. So it's the ideal after eliminating the first L variables. And I'd like to give an example, even though I'm not going to tell you exactly yet how to compute it, but just to show you what this ideal look like in a simple example. So I'm going to do it on the rationals, because then I can draw a picture and give you an idea. And just to make it simpler, I'm going to eliminate the variable z. So I'm going to put z at the beginning. In this case, the z is going to be the largest variable, and that's the one I'm going to eliminate. I use the Lex order. And the polynomials I want, the polynomials I want to consider, in this case, the surfaces that I'm going to consider are the following. I want to consider a elliptic paraboloid with equation z equals x squared over 9 plus y squared over 4, and a plane with equation z plus 2c plus x plus y equals 4. So even we can think of this in the reals, so that we can actually draw a picture of these. So we have an idea of how this looks like. I'm not going to try to draw it perfectly, but this is an elliptic paraboloid. So it's something like this. And then we have some plane that hopefully cuts this somewhere. So let's say there's some plane that perhaps cuts this ellipsoid. And we can imagine where this, how the plane is going to cut this paraboloid. It's going to be an ellipse. And when we think about the system of equations and its solutions, what we're thinking of is precisely on this set of solutions of the system of equations. So the ideal we're talking about here is the ideal generated by these two equations. I'm going to write them as polynomials. So I'm going to write them as z minus x squared over 9 minus y squared over 4 and 2c plus x plus y minus 4. And we're looking for the variety of this ideal, which is the set of all points x, y, z that satisfy both equations simultaneously. So now, magically, I'm gonna tell you what is the elimination ideal, the first elimination ideal. So I1, when we eliminate z, the variable z, what do we get? What we get is the following. We get x squared plus 9/2 of x plus 9/4 of y squared plus 9/2 of y minus 18. We get an ideal that on the last two variables, x and y, so it's an ideal that lives in the polynomial ring in x and y. And from the equation, we can tell what this is, right? This is, I mean, the variety of this one is the set of solutions can be described as an ellipse. It's an ellipse in xy. So if we draw this in the xy plane, it's gonna look, it's not centered, but it's some ellipse in the xy plane. So this, what we're saying is if we eliminate one variable, we get an ellipse in the xy plane, right? So this most likely has something to do with projecting this solution, this blue solution, on the xy plane. So if we have the xy plane here, so let's say we have x here, sorry, x here, y here, and z here, and we project that curve that describes the solution into the xy plane, what we're gonna get is an ellipse which is described by this equation. So in fact, the elimination ideal has a lot to do with the projection into the last variables. It's not quite exactly the same thing, but it has something to do with it. And this also suggests how to solve the equations. If we eliminate one variable, then we can take each solution in the xy plane and try to lift it to the next variable. And to do that, we include the rest of the variables, the rest of the equations to try to get it. This solution probably lifts to a solution up here. Each solution here corresponds to a solution of the actual equations, right? So now, how do we compute this? How do we compute the elimination ideal? And the answer is using a Groebner basis in Lex order. So let I be an ideal in the polynomial ring, and let G be a Groebner basis of I with respect to Lex order. And let's suppose the variables are order x1, x2, x3 up to xn. Then for every L, the set of G intersected with the polynomial ring in the last n minus L variables. That's what we're calling GL. Is taking the elements from G and only including those that are written in the last n minus L variables. That set, G sub L, is a Groebner basis of the elimination ideal I sub L. So this is telling us something very nice. That if you have a Groebner basis in Lex order, all you have to do is pick from that Groebner basis the polynomials written in the last n minus L variables, and that is a Groebner basis of the elimination ideal. And not only for the last variable, but for every L. So by finding a Groebner basis for the whole ideal, we get Groebner basis for every elimination ideal. Let's prove this theorem. So we want to prove that GL is a Groebner basis of IL. So it's clearly a subset. So all we need to prove is that it generates all the leading terms. Since GL is contained in I sub L, it suffices to show that they generate all the leading terms of the elimination ideal. This contention is immediate because it's a subset. What we really want is to show that every leading term in the elimination ideal can be found as a leading term as a leading term of the ideal generated by the leading terms of the GIs. So let's pick, let F be an arbitrary element in the elimination ideal I sub L. And let's try to show that there exists an element in G sub L whose leading terms divides the leading term of F. Now, since by hypothesis G is a Groebner basis, then G, there exists an element G in the Groebner basis that divides the leading term of F. Since G is a Groebner basis of I, and F is an element in I, there exists G in G such that the leading term of G divides the leading term of F. But that's not enough. We want G to be in G sub L. All we know so far is that G is in capital G. Now, the thing is that F is an element also in I sub L. Since F is an element written in just the last variables, x L plus 1 up to x n, then its leading term then every term is written in these variables, in particular its leading term. And since the leading term of G divides the leading term of F, then the leading term of G is also written only on those variables. But now, notice that G, that the order of the Groebner basis, on which we computed the Groebner basis, is the lexicographic order. Since the leading term is written in these variables, and we're considering the lexicographic order, then not only the leading term, but all its terms are on those variables. If there were any other variable involved in G, then that would not be its leading term. That would be its leading term. If you had a larger variable, then that would be the leading term. But since the leading term is in these variables, then every term in G is there. Since the order is lex, every monomial in G is in those variables. Hence, G is a polynomial in the polynomial ring in the last n minus n variables. So G, therefore, G is in the G. We know that G is in G, but it's also in the polynomial ring in the last n minus L variables. Therefore, G is in G sub L. That's how we define G sub L. Notice that here it was very important that we use the lexicographic order. Otherwise, this last step would not be possible. Now, are there any questions before we continue? Maybe I should mention something here. Computing a Groebner basis in lexicographic order is usually very expensive. Commonly, what we do is we first compute a Groebner basis in some graded order, like graded lexicographic or graded reverse lexicographic. And then there's an algorithm to transform this Groebner basis from one order to another to get this Groebner basis in the lexicographic order. WRT with respect to. Sorry, that's an abbreviation. So somebody asked what WRT is. It's with respect to lexicographic order. Yes, and again, as last time, if you have any questions, please ask them. I'll be happy to try to answer them. All right. So there are other results that are relevant, but I'm not going to cover here, that are relevant to the problem of solving the system of equations. One is the extension theorem, which gives conditions on when a partial solution can be extended. So it's not always true that when you get a solution on the projection, you can lift it to a solution on the actual space you're looking for. It's not always possible. The extension theorem gives some conditions for algebraically closed fields. The closure theorem tells us something about this, tell us something about the relation between the projection and the elimination ideal. They are not always the same. The projection may be smaller. The projection may be bigger, but what we know is that the variety of the elimination ideal is the smallest affine variety containing the projection. So the projection may be smaller, but it is contained in a set that is algebraic. That is but again, this is true only for algebraically closed fields. It may happen that they do not coincide exactly, and they actually may be a little bit far away, but it's still there's a close relationship with them. So again, the variety of the elimination ideal is the smallest affine variety containing the projection. That's good. That's at least gives us a bound. And for many cases, that bound is very good. But again, this is an algebraically closed field. Finally, the Nullstellen Satz tells us precisely what the ideal of the variety of the ideal is. So one would hope that if you take an ideal I, you find all solutions, so the variety V sub I, and then you find I of that, so the ideal form by all polynomials that vanish on those points. You would hope that they are exactly the same ideal you started with. And it's not necessarily. And the answer is, for an algebraically closed field, what you get is the radical of the ideal, which is pretty good. It's close enough. It's as good as you get. If you started with a radical ideal to begin with, then it is true that you get the radical. And this has some importance in because it gives you a nice algebraic relation. But again, it's for algebraically closed fields. And it's not so important for solving the system of polynomial equations. Okay. All right. So at the end of the notes of the slides, I'm always going to leave the references. And I'm hoping that these slides will be available on the website after the recording is uploaded. So you can go back and take a look at some of the references that I used. All right. Now, I'm going to start a new topic here. So I'm going to change. Maybe before I do that, let me do something here. Let me show you that this actually works. So let's do some computation of this. So let's take the example we did, let's plug it into a software, let's get the Groebner basis, and let's see that we actually get what we expected. Just to see that these things actually work. All right, so I actually prepared the example here. I'm going to run it on Magma. It's very simple code to do it. Here I defined the field to be a rational field. It can be reals, it can be anything, but in this case, it's easier to do it with the rationals. I define a polynomial ring starting with z and then with x and y. It has 3 variables. It's over the field by defined, and it's going to be using lexicographic order. Then I included the 2 polynomials, z minus 1/4 of y squared minus 1/9 of x squared, and 2z minus 4 plus y plus x. And then I'm going to compute the Groebner basis of f, and I'm going to print g. All right. I'm doing this on Magma, which is a software to do algebra. This is a student version that I have, but you can also do this in Sage Math, or you can do it in any other software that does a little bit of algebra. And here's what we got. So G, after computing the Groebner basis, is these new basis. And notice that the second polynomial, x squared 9/2 of x, 9/4 of y squared, 9/2 of y minus 18, it doesn't have z. This is precisely what we wanted. The last equation does not contain z. So this corresponds to the projection over the xy on the xy plane of the whole variety. And these 2 polynomials are a whole basis for the ideal. So if we want a solution, we can take a solution from here and lift it to the other one, which is a plane which is the plane we started with. It's exactly the same plane. So you lift it to this plane to get the solutions on the whole thing. All right. Since this is a good place to take a short break, I'm gonna take a short break now. And when we come back, we continue with the second part. In this part, linear algebra enters the picture. So it's 3:49 right now. We come back in 6 minutes, say 3:55, right? Welcome back. To remind you of the mini course we're doing and what are the topics we're covering. We started with a motivation, then Groebner basis and elimination theory, and now we're going to start talking about linear algebra to compute Groebner basis. And then in the last 2 sessions, we're going to talk about syzygies and the complexity of Groebner basis computation. So in this second part, we're going to talk about the XL algorithm, about the theoretical foundations for that algorithm to work. And we're going to talk about the F4 algorithm. So most likely we will cover 1 and 2 today, and then we will do the F4 algorithm tomorrow. So let's recall the Buchberger algorithm to compute a Groebner basis. Remember that we started with a basis F for the ideal. We consider all pairs of elements from G. And then while there are elements in B, we pick one, we remove it from the set of pairs, we compute the S polynomial, then we compute the normal form, that is the remainder under division by G of that S polynomial, and we, if that remainder is different from 0, we add that element to the basis. And we consider new pairs of that element with the old elements in the basis. Now, I'd like to see as a general framework of computing Groebner bases, something like this. So what we're trying to do is make sure that the ideal generated by the leading monomials of the GIs is equal, fills up, has all the ideals, all the leading monomials of the ideal. That's what we're trying to do. So what we do is we put in this beaker a basis. We have a basis for the ideal. And then we have some way to produce new elements in the ideal that add new leading terms to the ideal generated by the leading terms. We add those new elements to our mix. We have a way of mixing things around so that things are somehow reduced. And then we have a way to verify that we finally got a Groebner basis. In the Buchberger algorithm, the way to produce new polynomials is using S polynomials. And reducing, the way to reduce them is doing the division algorithm. And then the way to test that we have a Groebner basis is to make sure we go through all the pairs and none of them, and all of them reduce to 0. But we can do this in other ways. And here's the idea of the extended linearization algorithm. This is called XL, extended linearization. Here I'm citing when they gave the name XL to this algorithm. This is a paper with Courtois and I think it was Shamir and Pataran, and this was from 2000. But actually, the theory behind this is what was there before this was described in this way. The theory can be tracked back to Daniel Lazard from the 80s. And we will get to Lazard later, but for now, let me call it the XL algorithm, extended linearization. And the idea is the following. Let's say we want to find a Groebner basis for this set of polynomials. We have 3 polynomials in 2 variables, x and y. So we're going to first linearize that system. And by linearizing, I mean we're going to consider the matrix of the coefficients. It's like we identify each column with one monomial and each row with one of the polynomials. In a sense, it's as if we were considering each monomial as a separate variable. And we form this matrix of coefficients. We will later call that the Macaulay matrix. We'll get there, but let's consider this for a second. Now, we can do Gaussian elimination on that matrix And we're going to get something like this. Now, we can take each of those rows and think about them again as polynomials. And each of those rows corresponds to a polynomial in the ideal generated by the three original polynomials. And since all we did was row operations, they still generate the same ideal. So the ideal is the same. We have a slightly better basis in a way, but it's not a Groebner basis. It's not a Groebner basis, and we will see how, but we have different leading monomials at least. The three polynomials now have different leading terms, and that's important also. But let's say we know it's not a Groebner basis. Now, can we get more polynomials? How we can get more polynomials? So one way to do it is we take each of the original polynomials and we multiply them by variables. Let's say the first one we multiply by x to form this new polynomial, x cubed, 2x squared y, 3x, y squared, 4x. And this is an element in the ideal. And we can do this with every variable and with every one of the three, every polynomial. And so we're going to get 6 new polynomials, which correspond to the first 6 rows of this matrix. These are the 6 polynomials produced by multiplying the original polynomials by variables. And here below are the 3 original polynomials. Now, we can again do Gaussian elimination on this larger matrix. And okay, notice first that, so I organized this by degrees. The first part is degree 3, the second part degree 2, the third part degree 1, and the same on the rows, right? This block down here would be a block of zeros, right? So now, when we do Gaussian elimination, we will hopefully get something like this. And we got an echelon form, and it's nice. Notice that the last 2 polynomials actually dropped in degree. They were degree 2 polynomials, but now they happen to be of degree 1. There was a drop in degree here. I think there are some questions. Can you send me these notes via mail? I'm gonna try to get the notes on the website where the video will be recorded. I think that's easier for me. It's harder to pick up some emails, some addresses here. Also, you can look me up and send me an email, and I can send you the slides directly, but I cannot do it here. Like, try to copy and paste those email addresses right now. Right. So, as I was saying, the last 2 polynomials here dropped in degree. And they are very nice because they are linear. They correspond to linear polynomials. By doing this, we have found a couple of linear polynomials in our ideal. And since this is a system in 2 variables, well, these 2 equations will give you all solutions. Well, they will give you the unique solution. If we get something like this, we found the solution to the system of polynomial equations. in general, we increase, we extend to some degree, and then we do Gaussian elimination in this huge matrix until we are done, until we find a Groebner basis, or until we find a solution to the system. And this somehow corresponds to the general framework that I presented before. Here, the way to produce new polynomials is multiply by variables, the previous ones. The way to mix the polynomials in the basis is to do Gaussian elimination. And what we don't have very clearly now is a way to check that we have found a Groebner basis. I will leave it there, and I will talk about that in a moment. Now, as I said, maybe any questions before I continue? Does the idea I just presented make sense? Okay, so I'm gonna continue then. So this idea, as I said, goes back to Lazard in the 80s. And the key observation of Lazard was that a homogeneous ideal is actually a k-vector space. It's a vector space over the finite field. And its degree D component is a finite dimensional subspace. And here, I think I have to clarify something before I continue. So the notation is gonna get mixed up, because here, what I mean by I sub D is not the elimination ideal, but the degree D component of the ideal. And that is the polynomials in the ideal of degree exactly D. The polynomials in the ideal of degree exactly D are a finite dimensional subspace of that larger vector space. This is true in the homogeneous case. In the affine case, if we don't have homogeneous, we can look at I less or equal to D. We can look at the polynomials of degree less or equal to D in the ideal, and they form a finite dimensional vector space over the field. So doing linear algebra, doing Gaussian elimination, we can compute basis for these things. Now, what I'm gonna do in the next is to give a solid ground to this theory. So explain why, in general, this works. Why you can find a Groebner basis by doing linear algebra on this Macaulay matrix, which is the matrix of the polynomials up to a certain degree. Here is a definition. Let V be a K subspace of the polynomial ring. So I'm saying let's suppose V is any subspace of the polynomial ring. And I'm talking about the subspace as a vector space over the field. A subset B of V of the vector space is called a staggered linear basis if V generates the subspace V and B is staggered, which means that all the leading monomials of the element in B are different. Different elements have different leading monomials. Different elements have different leading monomials. And this is exactly what we achieved when we did Gaussian elimination. If you remember our example before, so something like this. If you look at these polynomials, you think of each of these as a polynomial, each has a different leading monomial. So this is a staggered linear basis of the original vector space generated by those polynomials. That's what staggered means. All right. And now we have the following result. Let B be a staggered linear basis for an ideal I, which is a vector space. Yes, I is a vector space. I know it is an ideal, but it can also be seen as a vector space. And let's suppose B is a staggered linear basis for an ideal. Then we can extract from that set B a Groebner basis. How? Well, let's pick elements in B so that for every pair of polynomials f and g, the leading monomial of g does not divide the leading monomial of f. So not only we want them to be different, but we want to make sure that one doesn't divide the other. We extract that, and that's a minimal Groebner basis for the idea. I haven't talked about what minimal means, but it's not really that important here. So I'm just going to prove that it is a Groebner basis. And there's a reciprocal to this theorem. So if you have a Groebner basis, you can compute a staggered linear basis from the Groebner basis. But I'm not interested in that either. I'm gonna just prove that from a staggered linear basis, you can compute a Groebner basis for the idea. So the first thing that is not obvious is that G is finite. So B may be infinite. In fact, if we have an ideal, a linear basis is definitely infinite. So it's not at all obvious that G is finite. And we know that a Groebner basis is finite. So the first thing we need to show is that G is actually finite. And it's finite because the ring of polynomials is Noetherian. G is finite because the polynomial ring is Noetherian. Which means that it cannot increase forever. If you have a chain of ideals, one contained in the other, then this chain must be finite. And you can see why this tells us that G is finite, because if you take two polynomials, let's say G1 and G2 in G, let's suppose they are different, two different polynomials, and you consider the ideal generated by the leading monomial of G1 and the one generated by the leading monomial of G1 and the leading monomial of G2, you notice that this one is strictly larger. This one is strictly contained in this one. And that's because of the condition that the leading monomials do not divide each other. Because the leading monomials of G1 and G2 do not divide each other, when you include another one, you necessarily increase the monomial ideal. So if you start adding one at a time of this G as leading monomials to the ideal, you're gonna get strictly increasing ideals, and this cannot go forever. It has to stabilize, and therefore G must be finite. Now, we want to show that that's a Groebner basis. So we're going to take an element, as we have done several times now. We're going to take an element in the ideal, and we're going to show that there's an element in G whose leading monomial divides the leading monomial of F. So let F be an arbitrary element in the ideal. Since B is a staggered linear basis, we can write F in terms of the F sub i's, right? So since B is a basis, and it's a basis in the sense of a vector space. So I'm going to say here a K basis to emphasize that. Since B is a K basis, there exists, I can write F as a sum, as a finite sum, in fact, I equals 1 to M of some coefficient C sub I, X sub i's, with the C sub i's in K and the F sub i's in B. It's finite because it's a basis. The coefficients are in K because it's a K basis. And now, if we look at the leading monomial of F, that leading monomial has to be happening in some F sub I. Because all of the leading monomials are different, it must be happening in one of those. Let's assume, just for simplicity, that they are all different. Well, actually, it's not necessary. Since B is staggered, there exists some index j such that the leading monomial of f coincides with the leading monomial of fj. The leading monomial of f has to be happening in one of those f sub i's. Actually, maybe for that it's easier to make sure that this is different from 0. So if you look at the maximum leading monomial of the f sub i's, it has to be exactly. So this is equal to the maximum among the i's of the leading monomials of the f sub i's. And this is precisely the leading monomial of one of them. Right? All of the leading monomials are different. The max has to coincide with the leading monomial of f, and it's the leading monomial of fj, of some fj. Well, if fj happens to be part of g, well, we're done. And otherwise, if it's not in G, by the way we constructed G, there must be some element in G whose leading monomial divides the leading monomial of fj. Right? Otherwise, it would have been included there. If there was no leading monomial in B that divided the leading monomial of fj, then fj had to be in G. So if it's not in G, there must be some leading monomial, some polynomial h in B that whose leading monomial divides the leading monomial of fj. Now, it may be that this new h, this h, it's in the basis. If not, we can continue going back. So we can iterate until we find an element. We can iterate the process until we find G star in G, such that the leading monomial of G star divides the leading monomial of F. And this is possible. This process will stop at some point because we're talking about a total order and a well order. It's a well order, so this cannot go on forever. You cannot find monomials that divide and divide and divide and never get to actually a polynomial in G. right? Are there any questions? Okay, so if we had a staggered linear basis for an ideal, we could construct a Groebner basis. But this doesn't really give us an algorithm, right? Well, to begin with, I is an infinite dimension vector space. So B is probably infinite. We cannot really get an infinite basis to be able to then find this G. So we cannot this seems to be helpless. However, the trick is that we can do this 1 degree at a time. So because we can define a notion of the Groebner basis and use the same idea to construct the Groebner basis. So Groebner basis up to a certain degree. And once we have that, we will see that eventually there's going to be some degree in which we actually get a Groebner basis. All right? So let I be an ideal and G a set of generators of that ideal. G is called a D Groebner basis. A D Groebner basis of the ideal I if the leading monomials of the ideal up to degree D is precisely the ideal generated by the leading monomials of the G1 through Gm. What I mean here by R less or equal to D is the polynomial ring, but only looking at the polynomials of degree less or equal to D. So the polynomial ring is a graded, can be seen as a graded ring. We can consider pieces and they are disjoint. So now we can do the same thing, but with a D Groebner basis. So if we had a staggered linear basis for I less or equal to D, then from that staggered linear basis, we can construct a D Groebner basis for the idea. How? In this way. The same thing, we pick elements so that they don't divide each other's leading monomials. And the good thing here is that, in fact, this is a finite dimensional vector space. It's not infinite. And then it should have a finite basis. And from a finite basis, we can hope to find this Groebner basis, this D Groebner basis. I'm not going to do the proof because the proof is very similar to what we did in the general case. Now, what is crucial here is that from a D Groebner basis, we can get to a full Groebner basis. Let I be an ideal in the polynomial ring. There exists a degree D sub 0 such that for every D larger or equal to D0, every D Groebner basis of I is a Groebner basis of I. In other words, there's a degree at which a D Groebner basis is a Groebner basis. And in fact, for every D larger than that, it's still the case. Let's prove this proposition because it's important. It's going to give us what we need in order to be able to use, to make sure that doing this Gaussian elimination 1 degree at a time, we will eventually find a full Groebner basis. Again, we're going to use the fact that the ring is not Ethereum. So, since the ring is not Ethereum, and we consider the following sequence of the following chain of ideals. Let's consider this chain. So leading monomials of I intersected with R0. And this is the polynomials of degree 0. That one is contained in the ideal generated by the leading monomials of I intersected with R less or equal to 1. And so on. So less or equal to 1, less or equal to 2, and so on. These are all ideals. Sorry, these are all ideals. Yes, they are ideals. This ideal generated by, and they are contained one inside the other. So that sequence must stabilize. So that at some degree D, you get you don't grow anymore. And when so there exists some D0 such that the ideal generated by the leading monomials of I which is equal to the ideal generated by the leading monomials I intersected with the union of all R sub L's, let's say L equals 0 to infinity, it's actually equal to the ideal generated by the leading monomials of I intersected with R0. Sorry, RD0, right? Because this chain cannot grow forever, there must be a point where it stabilizes, and that D0, for that D0, you get this equality here. You get that union, everything else, you don't grow anymore. You get everything you can get up to RD0. Now, then, for any D larger or equal to D0, let's suppose we have a D Groebner basis. Let's suppose G is a D Groebner basis for some D larger or equal to D. That's what the hypothesis is saying. Then the leading monomials I, which are equal to the ideal, generated by the leading monomials of I intersected with R D sub 0, which is equal to, because it stabilizes there, leading monomials of I intersected with RD, D is larger or equal to D0, and it's contained because we have a D Groebner basis. This is definitely contained in the leading monomials of G. So, since G is a Groebner basis, a D Groebner basis, the definition of D Groebner basis says that we get all the leading monomials up to degree D in G. So all of these are contained in the leading monomials of G, and therefore we get the whole containment. The leading monomials of phi are all contained in the leading monomials of G. It's actually contained. That's all we need.
Sir, I want to ask something. Hello?
Yes, please do.
Below the sentence must stabilize, so there exists D0 such that why the ideal generated by the leading monomial of I equal to the ideal generated by the leading monomial of I intersect that union.
So this gets to a point where it doesn't grow anymore, this chain. And notice that the union, they are they're one containing the other, and it's also true that R0 is containing R less or equal to 1, R less or equal to 1/2, and so less or equal to 2, and so on. So at the point where it doesn't grow anymore, you already got everything you can get from there on. This is as far you have to go to get the whole set, because this chain stabilizes at RD0. Does that make sense?
Yes, but I mean, why LMI equal to LMI intersect the union of
This is polynomial.
Yes, I mean that.
Okay. Okay. This is just trivial. So this is simply this is another way to write this thing here. If you get the union of all RL, so what I'm doing that there is just R0 union R less or equal to 1 union R less or equal to 2 union, and so on through all the positive integers. So this is simply the whole ring. This is the whole ring of polynomials. That union is the whole ring. So this intersection is just taking the leading monomials of I. I'm intersecting with the ring.
Okay, I understand. Thank you.
Yeah, you're welcome. And thank you for asking. All right. So this should give us an idea of how to construct a Groebner base. These two results together suggest a way to compute a Groebner base. You go, let's say, at degree 1. You start at degree 1. You find a staggered linear basis. From that, you get a 1 Groebner basis. If that 1 Groebner basis is a Groebner basis, you're done. If not, go to the next degree, d equal 2. Compute a staggered basis for I less or equal to 2. Then compute a 2 Groebner basis. If that 2 Groebner basis happens to be a Groebner basis, you're done. If not, keep going up. Linear basis, staggered linear basis, d Groebner basis, and iterate until you get to this magic degree d0, where the whole thing is stabilized. Yeah, it sort of solves the problem. If we had a way to know where to stop, we will get back to that in a moment. Just to formalize this, let's define what a Macaulay matrix is. So within a set of polynomials F in a polynomial ring, we will call a Macaulay matrix of F in degree D, and will be denoted M sub dF, is the matrix whose columns are indexed by monomials of degree less or equal to D, and whose rows corresponds to polynomials of the form a monomial multiplied by a polynomial in F, so that the degree of that product is exactly D. Similarly, we can define the Macaulay matrix up to degree D. So here we were saying that we're only including polynomials of degree exactly D, but we could include polynomials of degree up to D, and we will denote that this way. And you can also go back if you had a matrix where the columns are indexed by monomials, and you can get back the polynomials. And that I will denote. So given a matrix whose columns are indexed by monomials, the polynomial representation of M will be denoted as P of M. And what is nice about this is that given a set of homogeneous polynomials, then these polynomials, the polynomials that are obtained in this form, are a linear basis of the ideal up to degree D. If the polynomials are homogeneous, and that's because when the polynomials are homogeneous, there's no drop in degree. The polynomials stay at 1 degree. So all the polynomials you can obtain are there at that degree. So we can find an echelon form of the Macaulay matrix up to degree D, and that happens to be exactly a staggered linear basis for the ideal up to degree D. And that gives us an algorithm to compute a Groebner basis, which, if you want, you can call it Lazard's algorithm or the Excel algorithm. At least this is the homogeneous case. And is precisely what we have already said. Let's start with a list of polynomials P. Let's compute the echelon form of that list of polynomials. And by echelon form, I mean form the Macaulay matrix and do Gaussian elimination on that matrix. Then consider all I'm doing here a specific case. I'm supposing that all the polynomials in P are of the same degree, so that I can consider 1 degree at a time, in a simpler way. But this can be generalized. So let's suppose that P is a list of polynomials, that they are homogeneous and they are all of the same degree. And then you consider pairs of variables and polynomials, and while no solution is found, take each polynomial G, multiply it by a variable X, then with that form a larger system, then construct H that way. So these are variables times polynomials, then do the echelon form of that, of H union G, and then extract any new leading monomials that appear in that process. I'm going to call that H tilde plus. So do Gaussian elimination, extract new leading monomials, and then add those leading monomials to G. And then consider next all pairs of variable and the new polynomials, and continue that way until you find a solution. So the notation may seem a little strange, but it's going to be helpful when we jump to the F4 algorithm. For now, all we're doing is construct the Macaulay matrix, multiply by variables, do Gaussian elimination, and continue that way. Also note that I don't have to always multiply the original polynomials, but I only multiply the new polynomials. Only the new polynomials are the ones that are multiplied. Have just 5 minutes left, and I'm gonna quickly talk about the non-homogeneous case to finish this. So in the, this worked for the homogeneous case, what I just mentioned. In the non-homogeneous case, we have to be a little bit more careful because things drop in degree, and we can do it something like this. Let F be a set of polynomials, and let's consider the Macaulay matrix up to degree D. Let's do an echelon form on that matrix. Let's call it M tilde, and then let's add new rows to M tilde for every polynomial and for every monomial, so that the degree of UF is less or equal to D. And UF was not already in the row span of M tilde, on the row space of M tilde. So what I mean here is we're gonna add elements to M tilde of the form UF, where U is a monomial and F is a polynomial that was already here, but that when we multiply it by a monomial, is not in the span of the rows of the matrix already. So we are somehow, what we're doing here is when polynomials drop in degree, we multiply them before we go to a further degree. And this way we're kind of saturating the degree D. Repeat this process successfully until there's nothing more to add, until there's nothing that drops in degree and we can add. And we will refer to this as the saturated Macaulay matrix. We will denote it as SM less or equal to D of F. And it so happens that there exists an integer D0 such that for every D larger or equal to D0, the polynomials in the saturated Macaulay matrix is a staggered linear basis for the ideal up to degree D. So this actually leads to a staggered linear basis and eventually to a Groebner basis, therefore. And that's, in a sense, what we call the mutant Excel algorithm is basically the same idea as before, except that we take at each step the minimum degree, and we work on that minimum degree of the pairs that we are considering. So when we're dealing with non-homogeneous polynomials, we may have a loop inside where we don't increase degree yet, but we keep saturating the Macaulay matrix, and that's what we're doing here. We do like that saturation before moving on to the next degree. Since the time's up, I'm gonna leave it there. So we've seen today how a Groebner basis is useful for solving a system of polynomial equations. And then we have shown that we can compute a Groebner basis doing linear algebra on a 1 degree at a time on a Macaulay matrix. This is very useful because we have transformed a problem that was about polynomials and S-polynomials and division algorithm. We have switched to a problem of linear algebra, which is done using Gaussian elimination, and there are very good algorithms to do Gaussian elimination. There's still many redundancy here, and we haven't actually talked about how to stop. I keep saying here, while no solution is found. So next time we will talk about how to stop what can be a termination condition, and we will talk about the F4 algorithm, which is something in between the Buchberger algorithm and the Excel algorithm. So using pairs in a way, using S polynomials, and then also in a way using linear algebra. So that's it for today. Thank you very much. I'll see you tomorrow.